Present video is on shift registers, and which is part 3 of sequential circuits. Part 1 and part 2 have been covered in earlier videos. To summarize this video, registers find applications in a variety of digital systems, including microprocessors. For example, Intel 8085 microprocessor contains 7 8-bit registers as a general purpose registers and 5 1-bit registers, which are named as flags. So these registers are classified according to whether their input and outputs are parallel, serial, or both. There are 4 types like serial input, serial output, serial input, parallel output, parallel input, serial output, and parallel input, parallel output. These shift registers also find applications as counters. 2 important shift register counters are ring counters and Johnson counters. A ring counter is an n-bit shift register that recirculates the single one continually. It acts as a mod n counter. Johnson counter is modified ring counter that operates as mod 2n counter. These find applications in generation of timing sequences or time delays respectively. Now we'll start the video presentation. Let us see the first slide, first sheet here. Here, as usual, we said it's a shift register with sequential circuit part 3. What is a register? We want to know. So register is a collection of flip-flops arranged to store a binary data or binary information. This binary information and data can be loaded in parallel or in serial. In these registers, there is no sequence of states like we have in counters, and here data can be shifted by 1 bit to the right side or to the left. Okay. Then there are registers of the type like memory register. Memory register is the register which stores the binary information, and shift registers are the registers that shift the information from left to right or right to left, or they shift the information to left or to right, you can say. Now we'll see a very simple shift register arrangement. This shift register is said to be a 4-bit shift register. You see, it uses 4 flip-flops, and you can observe here this clock signal is synchronous. That means to all these flip-flops the clock is applied simultaneously, and the data like D1, D2, D3, D4 are the data input, and the data on a single clock gets applied to these flip-flops parallelly. So it can be shifted parallelly here, and you can see here it could be the data could shift either parallelly, like it could be, or serially. Serial shifting 1 bit at a time. When the data is shifting 1 bit at a time, that means first there is a serial data, and 1 by 1 bit the data is going into the register. Then it's serial shifting, so 1 bit at a time. And when all the data is entered into the register, then that is said to be a parallel shifting of data. Okay, now we'll see here shift registers. As we said earlier, they have been classified like 4 types depending on how the information is entered into the shift register. So these 4 types are being indicated here, 1, 2, 3, 4 types. Here, if we notice that the first block here indicates serial in, serial output, SISO, and this is an n-bit register, and data is entered serially into the register. And it's taken out also serially from this register. The other arrangement could be a serial in, parallel out. Here the data is entered here serially, 1 bit by 1 bit, and it is taken out parallelly, all the bits put together the same time. Then this is parallel in, serial out. This is said to be PISO, and here you can notice here this is parallel in and this is serial out, and this is parallel in and parallel out. Means data is entered parallelly and data is coming out also parallelly. Okay, so these are the 4 different types of arrangements for the data to be entered into the shift register and how it is to be taken out from the shift register. Now we'll take a simple example of a SISO register, that means serial input, serial output register. Here this register you can notice here I have taken an example of a 4-bit data, and this is a 4-bit register, and whenever the first clock signal comes, the data is entered from this 1101 into the shift register. So you can notice here this is MSB of the data, this is LSB of the data. Here shift register is MSB part, this is LSB part of the data. So this is basically an LSB of this data, so that gets entered into the shift register first, because this is shift right operation. So LSB will go to MSB here. So the input here will be 100. Okay. Now at the second clock, again the data which is left out here, now 010, this will remain, and this 0 will come back here. So now another data 0 has entered this, so this is 0100. Similarly, this third clock pulse will have data 1010, and the fourth clock pulse has entered the complete data, that is 1101. It's a complete data and is being entered into the shift register. So this is the way the data is shifted, and this is for a special case of shift right operation. So we can give the arrangement for both the operation. Here it says internal data shift MSB towards LSB. Here the shift is shift to right, this is MSB and this is LSB, so the shift is right. And serial in and the data is serial out. when this is there, so the data LSB here, LSB of this data will enter to MSB. So this is LSB to MSB. Now if there is a shift left operation of the shift register, then the data would be on this side and the MSB of the data would get entered into this shift register as LSB. So that's why we call it MSB to LSB. So depending upon the direction of shift in the shift register, it will determine that how the serial data would get entered into the shift register. Okay. Now the arrangement like parallel input, parallel output, the load to the parallel data bit is present to the respective flip-flops. So basically this parallel input, parallel output shift register is basically a storage register, not a shift register. Okay. Now we'll see various kinds of shift register, like bidirectional shift register, which can shift the data on either side, unidirectional shift register, and universal shift register has both the shift and parallel load capabilities. Okay, they can shift the data left or right and parallel load capabilities. Shift register controls would have like what are the different controls of a shift register, like say a clear control which clears all the data, clock synchronous, that means clock is applied to all the flip-flops at the same time. It's a shift right and shift left control, whether you want to have the data to shift right or to the left. And then parallel load control is there, and n parallel output lines. Their parallel output lines are n. If it's a n bit register, so parallel output lines are n. Okay, now shift register counters. Now they are very important components. Like you can have a counter using the shift registers, and these shift counters or shift register counters are of feedback type. Here the last flip-flop output is connected to the first flip-flop in some way. So based on the way the connection is done, they are classified as ring counter. Here the output of the rightmost flip-flop is fed back to synchronous input of the leftmost flip-flop. In a Johnson counter or twisted ring counter, or it's also called a shift counter, inverted output is fed back to the input. So that is the basic difference in the Johnson and the ring counter, and that's why this Johnson counter is also said to be twisted ring counter. Okay, applications of ring counters are for generation of timing sequences, and Johnson counter can produce time delays in a given signal. Now we start with the ring counter. What is the ring counter? Here ring counter is also, as we said, is a shift register counter. Here output is fed back to the input. You can see here these are 4 flip-flops here. They are D type of flip-flop, this first, second, third and fourth. The output of this flip-flop, like here, fed back to the input of the first flip-flop, and this D input is the synchronous input of the flip-flop here. And we said this counter is self-starting. Why it is self-starting? We can see here, to make it a self-starting counter, what we have to do is we have connected the preset, which is active low input of the first flip-flop here, to initializing signal, and clear inputs of other flip-flops. They are all connected together here, and they are connected to initializing signal. And since these preset and clear are active low, so this will be operational. This condition will be operational when it is low. So when the low pulse comes at initializing signal, this flip-flop would be preset, means it will be set to 1 and others will be clear. So the output here, this will be 1, this will be 0, this will be 0, so this is 0. So initial count on this register is 1 0 0. So that's why it's said to be self-starting ring counter. And as you know, it's using the D flip-flops. This is using the D flip-flop, and in this a single 1 in the register is made to circulate here because it's a shift register. So this 1 0 0, this 1 will come here, then it will reach here, then here, like that. So single 1 in the register is made to circulate, so it's said to be a ring counter. Low initial signals, we have said all these sets of flip-flops and recess. The truth table for the ring counter is shown here. We can see the truth table here. You can see the first entry here for the truth table. When the initializing signal is low, that means it's independent of the clock signal, because this override signals, these signals, preset and clear signals, are overriding signals, so it does not depend whether the clock is present or not. It will give the outputs, like it will set the register to 1 0 0 0. Okay, QA would be, output would be 1, others would be 0. Now the INIT signal is high, so it is not active, and the clock comes, then there shifts to right. So the operation is like this is 0 1 0 0. The next class further 1 shifts to right, and so on. And then after the 4th clock pulse, it's again coming back to 1 0 0 0. So this is the arrangement of this ring counter. Since it's a 4-bit shift register, 4-bit register, so number of counts could be 16, but we are taking only 4 counts from this. So there is possibility of this counter to go to unwanted states. So you need self-correcting ring counter to avoid the invalid states to come in. Okay, now we'll talk about the Johnson counter. Johnson counter, as we said, is also said to be a Johnson counter or twisted ring counter. Why it is twisted ring? Because here the output is not connected from the Q output here, it is connected to complemented output here, so that's it said to be a twisted ring counter. And as usual, it's a D type of flip-flop. These are the corresponding outputs, QA, QB, QC and QD, and clock is synchronous and applied to all the flip-flops simultaneously, and it is edge-triggered clock, positive edge-triggered clock is applied, and this is a clock signal here. So we can see here inverted output is connected to the input, that we have already seen. It's very easy to analyze the operation, because whenever this output here is 0, this will be 1, so first clock pulse will take this to be 1. So these is a count sequence here, 0 0 0, all those zeros, then 1 0 0, then again it will go to 1 1 0 0, 1 1 1 0, and so on. These are the count sequence for the mod 8 counter here. The this Johnson counter gives us the square waveform, and modulus of Johnson counter is twice that of the number of flip-flops. That means here we are taking the number of states 8, while the ring counter has 4 states only while using the 4 flip-flops. So this needs less number of flip-flops, and requires decoding gates 1 per each count. Here decoding gates are needed for this kind of flip-flop, while the ring counter does not require any decoding gate. Now the last part here, we have given a table to compare the ring counter and the Johnson counter. Here number 1 is both ring counter and the Johnson counters are synchronous counters. That's the very important part. Now number 2 is that ring counter is a mod n counter, where n is the number of flip-flops and needs maximum number of flip-flops. So if it's 4 flip-flops, it's only 4 states, so it's the maximum number of flip-flops it needs. Okay, and mod 2n counter, that means it has more states than the ring counter. So mod 2n counter is less than ring counter. It needs flip-flop less than ring counter, but more than the binary counters. Okay, needs no decoding circuitry that we have seen, and more circuitry is needed, decoding circuitry is needed for Johnson counter. It's more than ring counter but less than the binary counter. Now the other part is output. It's not a square wave, where the output here for Johnson counter is a square wave, and this is basically based on the application. So used for this is used for the timing sequences for the control applications, and this produces delays here. So the output of each flip-flop is delayed by 1 clock pulse from the previous output. So depending upon the application, you can use either the ring counter or the Johnson counters. Although these counters have been very powerful and have been taken sometimes as a problem, gate problem, like AD and DA converter, there has been a problem. But most important part here is you are not to see the design of these counters. You have to only see is about what are the states these counters go to, and that is most important part for this. So that is all. Thank you very much.